Well, hello everyone. This is actually going to be the bonus quiz for 7.3. I wanted to start though with a problem that is going to be significant as we move forward in the class. What you're looking at here is a blog from the New York Times, and it deals with education. And every now and then a math teacher will write to this blog and give ideas for teaching and present problems that he thinks are important. And this one here is interesting in that it can be gotten at with our Chapter 7 knowledge, and it also points ahead to what's coming down the road in Chapter 9. Now, I'm going to solve this using an idea that's called orders of magnitude. Now, you may have heard this phrase as it's a math term that has seeped into general usage, and an order of magnitude is simply a multiplication of 10. So if somebody says something differs from something else by an order of magnitude, they mean by a power of 10. And that's really essentially what Chapter 9 is significantly about when we get to logarithms, powers of 10. And it's a tool that we'll be using a lot there in different applications. I wanted to use it to actually solve this and to tie it in with Chapter 7. Now, it's a word problem, and the essence of this word problem is really just this. The cost to run the New York City Marathon, he's talking about entrance fees, has risen from $80 in 2005 to $216 in 2012. And if around 50,000 people run in this year's marathon, how much will be collected in entrance fees? And that's a simple straight-on multiplication. If entrance fees are $216 per person, and if 50,000 people run in the marathon, you'd multiply these two together to get the answer. And so I thought we'd use our orders of magnitude and our laws of exponents to solve this. Now, I'm going to simplify 216. I'm going to round it down to 200, and then I'm going to write it in terms of exponents of 10, two orders of magnitude. This is 200. And then I'm going to multiply that by 50,000. And I want to write 50,000 in terms of powers of 10. And so I count the zeros. Each one will be an exponent. So there's 4 of them. So it's going to be 10 to the 4th. And so I can do the numbers. That's easy. It's 10. And then here we are in Chapter 7 with two bases that are the same, and we're multiplying. And that means we add the exponents. That's really the first law of exponents. And 2 plus 4 is 6. We have 10 times 10 to the 6th. Now, the slickest way to write a million is in fact 10 to the 6th. And a billion would be 10 to the 9th. And a trillion would be 10 to the 12th. And this is the way they're written in scientific notation and in scientific journals. So really what we have here is 10 million. And when we look at the answer space here, we do in fact see that an answer C is the correct answer. So without even touching a calculator, we solve this one with our laws of exponents. And that's a cool thing to do because it keeps us number smart. Now, let me get after the bonus quiz proper. I wanted to remind you though of where we are in a class. Keep in mind that I took PEMDAS and I changed it to PERMDAS. And the reason why I did that is because exponents are undone by roots, and roots are undone by exponents. These are inverse operations, just as multiplication and division and subtraction and addition are inverse operations. And so there's a symmetry to algebra, a beautiful symmetry, and we need to see that there are inverse operations here because that's where Chapter 7 is heading. We're going to undo equations with roots by taking the exponents of both sides. And we're going to do equations that have exponents by taking roots to both sides. And some of that is going to be happening here because I have roots and exponents, and something's going to get undone. There's a bit of a wrestling match going on here, and you'll see that in the final answer. There are at least 3 ways to solve this problem, and I wanted to take just a second to show the traditional way it's taught in classrooms all the way across the country. And that is, since we're taking the square root, we look for pairs or squares underneath the radical inside the radicand. I'll see students deconstruct these things so that they'll notice that x to the 4th has 2 perfect pairs, 2 perfect squares, and they'll write it like that. And then they'll do the same thing for y to the 11th. They'll deconstruct it into pairs, and they will have 5 pairs like so. But notice that's only power of 10, and so there's also another multiplication with a lonely y. And the idea here is that the square root undoes all squares, and they come out in front as multipliers. So these two are going to come out in terms of multipliers, and there's going to be 2 of them. And the square root will undo the squares on all of these things. And so we'll have 5 y's out front. And then we ask ourselves, what got left behind? And the only thing that got left behind is this lonely y here. And so a remains underneath the radical. And it's optional whether or not you want to put the 2 here, so I'm not going to do it. This is the answer using the slow sure technique taught all the way across America. Now, there's a slicker and quicker way to do this. And if you're going on with math, I want to show that to you. I'm going to leverage here the 3 laws of exponents. Now, I'm going to show you that there's actually a 4th law. Here, when the bases are the same and you're multiplying, you add the exponents. When the bases are the same and you're dividing, you subtract. And when you have powers to powers, you multiply. So addition, subtraction, multiplication, is there a time when you divide? And that's exactly where we're at right now. This is the moment when you divide. All I do is this. How many times does 2 go into 4? It goes in exactly twice. And there's no leftovers. So I could show x with no leftovers, but that doesn't make sense because any power of 0 is just 1. So we don't need to show that. And now we ask the same thing with y. 2 goes into 11 how many times? 5. And there's 1 left over. Notice the answers are the same, of course. And this is what we want to put into our MathXL. And so let me do that. X squared, y to the 5th. And then we want a radical with a y inside there. And so that's the answer for number 1. And so here's number 2. And this one is slightly more complicated. They want us to multiply and simplify these 2 radicals. Now, notice they're both cube roots, and as you could probably suspect, there's probably a rule for how to handle the fact when you have identical indexes, and there is. I call it going from a house divided to a house united, that we could write this as one big radical when the indexes are the same. And so I could, in fact, do that. Everything's going to be under a cube root, and since there's multiplication between them, there's going to be multiplication between this radicand and this radicand. And so we're going to have this situation here times b plus 3 to the 2nd power. And all of that is underneath this cube root. Now, inside here we have the same bases and we're multiplying, and so we can use the 1st law of exponents. That is, we can add those together. And if we do that, we get this cube root, and we're going to have b plus 3 to the 27th power. Now this is where it really makes sense to do the quick slick way of doing this. I'm not going to form a bunch of triplets here. I'm simply going to divide and ask myself, how many times does 3 go into 27? 9 times. And there's your answer right there. There is no leftovers, so there's not going to be anything underneath the radical. We don't even show it. And so this is the answer. And that is what we're going to type into MathXL. Now, one of the challenges with these problems is that there's many different ways to proceed to solution. And I suggest you don't shy from that, that you actually use that as a resource, that you can solve this another way. And you can check yourself to see if you get the same answer. Instead of going from a house divided to a house united, I'm going to go from roots to exponents. So I'm going to rewrite this like this. Now remember, it's to the 25th power, and that's in the numerator. And the denominator is this part right here. It's the index. And I'm going to rewrite this in terms of fractional exponents. And it will look like this. The power is the numerator, and the index of the root is the denominator. And now we have a situation here where we're multiplying, and the bases are the same, and so we can in fact add those exponents. And when we do that, we get the same base, of course, and then we add 25 thirds plus 2 thirds to get 27 thirds. But we always simplify fractions, and we're forced to do division even in this direction, and we get b plus 3 to the 9th, the same answer. So there are at least 2 ways to do this. And in one sense, I'm sorry to show you 2 techniques because I know that confuses some people. But in the other sense, it empowers you to be able to solve these different ways and to know the rules so well that you can shrug it and do them both ways. We said it was b plus 3 to the 9th power. And let's do a submit. And sure enough, we're good to go.